All right, good morning, folks, or whenever you choose to view this. Good afternoon, good evening, good middle of the night, whatever you choose is fine with these types of videos. So we're going to give this a try here. This is how, for the foreseeable future, we plan to do Friday lectures here in Met 103. The idea here, again, to give this a hybrid approach allows you to maybe keep a little bit more distancing, try to avoid as much contact when not necessary. And here now again you can view this if you're comfortable at the regular time, 8:40 or 10:20 depending on your class time, or if you're a night owl, give it a watch at 2 in the morning. Maybe it'll help with some insomnia. I'm not sure. But what we're going to generally do with these lectures is continue where we left off on Wednesday. There may be some slight differences in the two lectures, but I'm going to give it my best effort to be on par with both. And the way I typically run lecture, which you just don't understand yet because we're in the first week, is I will go over a slide or two. I understand that usually minutes 47 through 50 of a lecture are not necessarily when you're cued in the most to what's going on, and so a little refresher usually goes a long way. We'll keep this relatively light today, finish off what we've been talking about with regards to atmospheric structure and some of the measurements that we take in the atmosphere. We might touch upon energy. We may just leave some of that for Monday and maybe make a little bit longer of a lecture for next Friday. Again, the idea here is we're going to work probably anywhere between 30 and 60 minutes worth of videos. I'll encapsulate them in approximately 15-minute segments, so that way you can break it up and, again, kind of write down whatever notes you have. And by all means, we'll have a moment or two on Monday to take any overarching questions. There's always office hours, there's time in most labs for you to ask questions as well. So without further ado, we ended off here on Wednesday talking about pressure in the vertical. And the overarching idea with pressure in the vertical is that we can take it to the bank. It is always, always, always going to decrease with height. The idea that that pressure is going to be the mass of the atmosphere above you. So as we go higher and higher in the atmosphere, there's simply less mass. That gravitational pull down towards Earth means that we are going to have slowly but sure, actually quickly I should say, a decrease in pressure as we move up in the atmosphere. And this is why in this graphic, if you wanted to go for a climb to Mount Everest, you need to be in really good shape because you're dealing with significantly less atmosphere. And as we'll talk about shortly, because when we live in what's known as the homosphere, we're going to have significantly less oxygen in which we have to breathe. All right, get that slide going. Atmospheric temperature in the vertical, however, is, well, not as easy to deal with. It's not going to be the worst thing in the world, but it is something that we have to give thought and realize that it's not a slam dunk like pressure, that it always decreases with height. Temperature typically is going to be warmest down near sea level, down near Earth's surface, and we'll learn about this starting next week. The sun's energy, or the sun's incoming radiation, impacts Earth. The Earth absorbs that radiation and re-radiates it in a different portion of the electromagnetic spectrum. In short, we're going to have the most heating from below, and therefore usually near Earth's surface is where we find the warmest temperatures, but especially in certain times of the day that necessarily won't be the case. So to get a few terms out there, we're going to touch upon them now, and these will become more and more common as we move throughout the semester. When we talk about an atmospheric lapse rate, the rate at which temperature lapses or typically decreases as you go up in altitude. And so we may talk about a lapse rate of 7 degrees. And that's how meteorologists might slang it as the term of 7 degrees Celsius of cooling per kilometer. When will this become important? This is going to become particularly important as we work forward towards thunderstorms and stability, because if you have really steep lapse rates, in other words, cooling say 9 or 10 degrees Celsius per kilometer of altitude, it means that we can really grow the large cumulonimbus thunderstorms in the atmosphere. A couple other terms that we do use though are isothermal. Isothermal, iso meaning the same, thermal being temperature, and this is going to be whereas you typically cool with height, here we're going to actually keep the temperature the same as you go up with height. Not uncommon, but if we do see an isothermal layer in the atmosphere, it's usually pretty small. It's not going to be to where we go from the surface to Mount Everest and have the same temperature the entire way. Hint, it's also cold at the top of Mount Everest. So if you're really looking for that challenge, get in good shape and be ready for some chilly temps to climb Mount Everest. Inversion is a term that you're going to hear probably more frequently throughout this class. Inversion is when instead of decreasing with height, our temperature actually increases with height. This seems counterintuitive to what we just talked about, but what we can find is that in particular on clear, cool nights, not unlike what we've been experiencing so far, whereas we warm from below, we also can cool off quite rapidly by Earth's surface and sometimes get a little bit of a warm layer higher up. Not a huge deal most of the time, but in some instances an inversion can actually lead towards fog development in the morning hours. We'll learn a lot more about this as we get into stability, and inversion can also be a critical element, again, to the development of thunderstorms. More of a tease for the fact that most of you seem at least pretty interested in getting towards the thunderstorm and tornado portion of the class. So let's move forward. Layers of the atmosphere. This is stuff that you should definitely feel comfortable with before we get to that first midterm exam. And so when we talk about the layers of the atmosphere, we usually are going to refer to them as we move upward in the atmosphere. In other words, we're going to talk about the troposphere, then the stratosphere, then the mesosphere, and the thermosphere. And as you can see in the graphic, that's going from nearest to the surface as we approach outer space. And so this is a graphic you'll see on a number of the slides. I would strongly suggest feeling comfortable with this graphic as you do some of your studying. You can see that your thunderstorms and basically the weather we consider is all going to be in the troposphere, so we'll spend the majority of this class down in this troposphere. But other features such as the ozone max there in the stratosphere, big deal. We get up towards the thermosphere and you can see the auroras. If you've ever heard of the auroras or maybe been fortunate enough to see the auroras, beautiful features of color in the sky, high up, and what is causing these phenomena is actually some really interesting weather occurring on the surface of our sun. A couple other things to get out there when we talk about the vertical structure of the atmosphere. We can separate it, well, kind of just into two features, which would be the homosphere and the heterosphere. Homo meaning same, well-mixed portion of Earth's atmosphere, and that's going to be the lowest, approximately 80 kilometers of Earth's atmosphere. And so the majority of what was on the previous graphic, the troposphere, the stratosphere, and the mesosphere, are all going to be part of the homosphere. What does this mean? This means that concentration, that 78% nitrogen, that 21% oxygen, a little bit of argon, incredibly little bit of xenon and neon, we're going to have effectively the same concentration everywhere in the lowest 80 kilometers of the atmosphere. Generally speaking, that's a good thing. We can count on that 21-ish% of oxygen, which we need in order to live. Heterosphere, on the other hand, means that we're going to start to stratify. We're going to have gases in layers as we go higher and higher up in the atmosphere. Do you need to know a whole lot about what's going on in terms of this stratification up in the heterosphere? Not really, but it is something that you can read about. And one other thing you can note is that on the lower left of a number of these graphics, you'll see that there's a page number that you can go look up in your book to read a little bit more about this. The understanding here that by the end of this week, you should have at least considered, if not started, to read Chapter 1. Troposphere, let's get into it. And we're going to again spend time talking about all layers here. Troposphere far and away is going to be where we spend the majority of this class. But again, especially that stratosphere, that ozone layer becomes quite critical as we talk about certain features throughout the semester. And the reason we talk primarily about the troposphere, it's where we live and it's where weather occurs. And so when we talk about meteorology, we're primarily talking about changes in weather within the troposphere. Here, we typically see a decrease of temperature with height, and you can see that by the red line in this graphic. We may have temperatures again on a global scale, morning and night combined, maybe around 55 to 60. Doesn't mean that we can't find temperatures, you're 130 in Death Valley at times. Obviously, you have areas of the world that are well below zero, but what you can see here is that as you go up in the atmosphere, on a generalized sense, we cool off significantly. This will again make more sense as we get into the energy portion of the class next week. You can see the cooling rate, that lapse rate, that's about 6.5 degrees Celsius per kilometer or 1,000 meters. We will almost exclusively talk about lapse rates in degrees Celsius per kilometer over the course of this class, or at least degrees Celsius per meter. Lots of metric units, but we also have it there in degrees Fahrenheit per 1,000 feet. That becomes more critical as you work in a field such as aviation. We mentioned inversions, that warming with height, and I've kind of already talked about this portion. The idea that this is when the temperature is going to increase with height. It's going to be most common in the overnight hours, especially as you work towards daybreak, and this is because the cooling is more excessive down by the ground. We can find inversions throughout the troposphere. Usually they're relatively thin layers. And again, when we talk about inversions, we're often referring to a layer where it's really tough to get rising motion. This will make a lot more sense as we work later on in the semester, so I'm not going to get into great detail. But as I already alluded to, this becomes quite critical when we start to work our way towards thunderstorm development. One thing we'll throw out here now, and this isn't designed to get you stressed out, is the idea of thickness. And it's appropriate to talk about this now, even though we'll get into the nitty-gritty and the details of it later in the semester. We oftentimes will refer to the thickness of the troposphere. So if I actually go back up a slide, you can see here in this graphic, the troposphere typically extends up about 11 to 12 kilometers. But that's going to be variable. It's going to be thinner, maybe 9 kilometers, when you're in very cold areas, say the poles, especially we'll say northern Canada in wintertime. You may have a very thin troposphere or a very small thickness. Conversely, when you have warm air is going to expand, and so your troposphere is naturally going to be thicker. You can see the term tropopause, the highest point, or basically when we transition from the troposphere to the stratosphere. And so that tropopause will be at a higher height when the average temperature in the troposphere is thicker. The idea that cold air is going to be compressed and warm air is going to expand. And so we talk about this, that's really what it boils down to. You can see in that second bullet, warmer layers of the troposphere are thicker, so a warm troposphere is deeper than a cold troposphere. This is going to pop up on a lab, and we'll help you through it as need be. So we're going to try to help this make sense as we get later on in the semester, because one of the things we do in meteorology a lot is look at heights, and we'll talk about the 500 millibar height. And that is important because higher heights often correspond with maybe the heat wave that's currently going on out in the western United States, whereas when we get into wintertime, those heights are going to quickly decrease, and that's related to this thickness. So again, don't get too stressed about this. Hopefully that makes a little bit of sense, and we'll revisit it more down the road. Working up towards the stratosphere. Stratosphere is delineated by when we stop cooling with height. Again, you can see the temperatures in this schematic just being a rough estimate, maybe around -60 degrees Celsius as you work up towards the tropopause. A relatively quick decrease if you really look at the scale. But once we start to warm with height, we're entering the stratosphere. And we're not talking a small layer that's an inversion. We're talking about a deep layer of the atmosphere, but it is an inversion. The temperature is increasing with height. If you look, you can see by the top here of the stratosphere, again talking about a pause as we move from one layer of the atmosphere to another layer, we may be up to a real balmy 0 degrees Celsius. In fairness, that doesn't mean you would go to the top of the stratosphere and think, boy, it's really warm up here, because you have so much less air, it would still feel cold. But why does the temperature increase? Ozone. Ozone is, again, a gas, O3. We had that extra molecule or that extra atom of oxygen in there. And so our ozone molecules are going to be a different type of stability, and these are important up in the stratosphere because they are going to absorb ultraviolet energy. Ultraviolet energy is dangerous to human life. Without the ozone layer, we would, well, be at pretty significant risk for cancer. We would have to be even more protective than we are already when we go out into the sun. But what it means is that as the incoming ultraviolet energy is absorbed by the ozone layer there, somewhere around 25 kilometers above the sea level, it is going to cause the stratosphere to warm. That absorption causes a warming tendency. And so that's what is going on in the stratosphere. Mesosphere is getting high up there, above 50 kilometers, and we're back to cooling with height. It is going to be a chilly place up in the mesosphere. Notice the pressures. By the time you get to that stratopause, you're down around 1 millibar. In other words, 1/1000th of the atmosphere relative to sea level is now above you. So, no, you can't be up here and breathe. It would be impossible. And even down lower, even by the tropopause, you can see you're pretty low pressures, and that's why, again, we pressurize aircraft, and things going at high altitudes must have pressure suits, for instance. Pressure around 1 millibar, low air density, it's going to be really, really cold. We see here in the mesosphere in our schematic some meteors. This is effectively where meteors coming towards Earth would burn up. This is kind of where the atmosphere continues to protect us as humans, and so we don't have meteors crashing into Earth's surface all the time. Yay! And we'll end off this this video with the thermosphere. Yes, there's another one coming, don't worry. But the thermosphere is going to be back to where we increase with height, and so if you're looking at that red trace and thinking, whoo, is it toasty up in the thermosphere? The answer is no. You have so little air it would still be very, very cold. The density is effectively nothing, and as you kind of work your way out of the thermosphere, that's when you get towards outer space. And so here, this is where the auroras occur. What's happening here is you have charged particles that are leaving the sun, what's known as the solar wind. That's interacting with Earth's geomagnetic field, and that causes the auroras on certain instances. Yes, you can sometimes see the auroras this far south, but typically going to be something that occurs in the higher latitudes, either the North Pole, towards the North Pole, or the South Pole. And so we'll take a break from the video now. We will resume whenever you feel is the right time to resume, looking at other things with regards to Earth and the atmospheric structure, as well as measurements.